Okay, welcome everyone for the last ITC lunch of the semester. We're all going on a winter break in the coming weeks. We'll resume at the end of January, and we just had an excellent colloquium by Kartheik Iyer from Columbia. He will also be the first speaker today. How do you keep up with a million papers about billion-year or galaxy? Are you sure it's a million papers? I would be surprised.
As an astronomer, you get plus minus 3 decks.
Well, there are only a few thousand astronomers in the world, so and most of them produce less than 100 papers.
I mean, the overall corpus from ADS, I think, is like 6 million.
Really?
Across astrophysics, yeah.
Wow. Okay, we have a lot to read, I guess. The second speaker would be Richard Pan from Tufts. Where is Richard? Over there. Who will tell us about no environmental quenching in a Z equal 2.6 Proto cluster. Wow, that's a high ratio. And then Mesut Çalışkan from Johns Hopkins is visiting. Yeah. Who will tell us about beyond the power spectrum, non-Gaussianities in stochastic gravitational-wave backgrounds. We were supposed to have a fourth visitor from Dartmouth College, but that person was unable to come and just canceled at the last minute. So we will have 3 talks today, and that will give us a little more time for questions. Please go ahead, Patrick.
So I was told that just because someone cancelled doesn't mean I can take 20 minutes.
No.
I'm there.
You will benefit from more questions.
I don't want there to be plenty of discussion. So. Alright, since I'm from New York, I'm contractually obligated to use this font and color. Don't ask me why. But it's a pleasure to be here. I've tried to keep this talk as accessible as possible, but it is possible that some jargon creeps in, so please feel free to stop me and ask anything that's not clear at any point. This comes out of ongoing efforts since 2018-ish to try to keep up with the literature. I would say that I'm still failing, but I'm failing less badly than I was when I started. So this is part of a larger public talk that I gave, so I'm going to skip over some things that people here might already know about. So the part 1 was about billion-year-old galaxies, so it's about work that I'm doing with JWST, looking at star-forming clumps at very high redshift. And then the part 2 was talking about the lands of astronomy papers and how we can visualize the literature and then help that, use that to help us keep up with it. So I don't think I need to tell anyone here that finding relevant literature is not easy. It's something that you might have built up a library of over time as you continue doing research, as you grow more familiar with topics. But it's still not easy when you go to a new field or a new problem or out of domain in any way, or when you're trying to find something very specific that you are sure that you read but can't quite place. So there's a variety of different ways in which we find papers that are relevant. A lot of times it happens through friends of friends algorithms, much like we find halos, where we talk to someone and like, I'm working on this thing. Do you remember this paper that I saw talk about? And they're like, yeah, it's this group. But the nice thing, and citation graphs have been something that have been used a lot by systems like ADS when you do search by similarity. But since the neuro-linguistic programming, since NLP has been a thing, people have been trying to do something called semantic search, which is to ask a natural language question and then try to find matches in the corpus of literature that have the same semantic information. So not just a keyword match, not just a citation match, but a match in some encoding of meaning. So this has been sort of what this talk is going to be about. So this is from back in 2021, where I was building a system called Chaotic Neural that was trying to do this. using a NLP tool called doc2vec, which would take a document and then compress it into a set of numbers by building a dictionary and then seeing which words in that dictionary were occurring and co-occurring. And back then I was like, this is an emerging field, we have to do more, it's going to be great. And there was a lot of topological and graph-based methods that people were using to try to structure the space, including folks here who built Astrobird. So the basic concept is you want to do some kind of literature search where you take a paper or some part of a paper and convert it in a meaningful way into a set of numbers. And then you organize all of those numbers in manifolds so that whenever you have a question, you can take that question, project it into this manifold and find papers that live nearby, and then start from there in trying to get to your answer. So this is sort of like a zoom into this. So this was back when I did this only for galaxy evolution papers. And you can see each dot here is a single paper. And the set of red dots was sort of like the stuff that I was working on at that time. But if you ask it a question, like what's the search index of a disk galaxy, it finds primary sources, and then it tries to synthesize an answer from that. So this worked well enough, and I put this out as a literature search engine, stopped, forgot about it, until I was at a KITP workshop, and then I was telling someone about this, that like it's really hard to encode meaning into these embedding spaces. And a collaborator was like, yeah, but like, have you tried using these LLMs? And I was like, what's an LLM? Which, in this day and age feels like a very out of touch question. But so we got early access to GPT-4. We started building this based on GPT embeddings. And this was 2 years ago. When we started, we formed a reasonably big group and started putting together a bunch of people working on this and related topics. And it's grown even more in recent times. I'm not going to go into too much detail about this. So when we built this tool, we essentially did it in a very human-centric way. We weren't like, let's build something that does end-to-end papers. We wanted to build something that's explicitly useful as a research tool for astronomers. So we did a 4-week trial study with 40 astronomers that used a prototype of this, and then we did like interviews to figure out what they liked, what they didn't like, what they felt was needed. And so this was the team. I'm going to skip over a lot of this, but TLDR, we built this whole pipeline based on the feedback that we got to essentially start with an input query, do a bunch of filtering, eventually embed it through something like a GPT model, use that to retrieve papers, and then use those retrieved papers to try to come up with an answer. So this essentially lets us bypass a common problem that even today plagues large language models, which is hallucinations. So hallucinations are when the model so a large language model that's been trained on a huge corpus of information generally doesn't keep track of individual bits of information, so it can't do things like attribution. And it also can't say that when it generates the next string in a set of tokens, that information is factually correct, because that's not something that has been optimized to do. And so this mitigates it by grounding anything the LLM makes up in these retrieved papers that it comes up with. And so if you have something like this, where you read a press release about a high redshift rotationally supported galaxy, if you have the press release, you can go search for what paper this is based on, and you can find the press release, and then you can find the paper. But if you don't have the press release, then just searching for this doesn't really get you to that paper. And so this is where this tool that we made called Pathfinder helps, where you can put this query in natural language, and it retrieves papers, and it gives you an answer, and it both gives you a link to the retrieved paper and the answer. So this allows you to get to that when you don't have the source information. Since we put this out, it's been a bit over a year at this point. It's gotten over 100,000 hits, which has been really gratifying, like more than all of the other stuff that I do, which generally tends to be localized in galaxy evolution. This feels like a significant chunk of astronomers of our field has been using this, which is great. These days, models like Cloud can also do this to some extent because they have also exposed it to the internet and made it ground itself in real information, where it says, I'll search for the up-to-date information on this topic, and then it gives you the answer. But the nice thing that Pathfinder is able to do is not only give you the answer and the link, but also show you in the sort of space of astronomy papers where your query and its relevant papers live. So this has been a really good tool for me in terms of doing outreach especially, because I can go look at different parts of this astronomy galaxy manifold and see how they evolve, do all sorts of dynamical analysis on them. So Pathfinder at this point does a bunch of search and synthesis information. It also does, come back to this, it also does native multilingual translation, so you can ask it questions in a different language. It will find relevant papers in English, and then it will translate it back to give you the answer in the language that the query was asked in. So this has been great in terms of being able to especially go to other countries where undergrads might not have proficiency in English, but want to search for astronomical concepts and help them do that. And then it does things like simplify systematic concepts in a way that's accessible. So if you take this manifold in which the papers live and you make a heat map of it, you can see which parts are densely populated and have a lot of papers, which parts tend to be more fallow. And you can turn this into this visualization that I love using in talks, which essentially says, this is the land of astronomy papers. And you can explore this if you want by going to the QR code or the link over there. But it allows you to, see where different unified astronomy thesaurus concepts live, where different telescopes are currently producing papers, or where annual reviews in astronomy and astrophysics articles currently live. So I'm just going to keep this. And are we doing questions now or at the end? Yeah. Okay, perfect. So I'll just leave this, and that's a key for how to read this, where the mountains are like well-established areas, and the deep waters are where we still have to write papers.
Thank you so much. Well, indeed, we are in the business of expanding the landmass.
Yeah, very much.
But as much as AI sounds like a great opportunity for improving efficiency, I'm worried about several. I'll mention a few anecdotes. One is now people will read even less papers than they read before, because they will rely on this giving you all the references. You don't need to read them and just summarize for me what they say. And the problem with that is I work with an undergrad, and then I look at the paper, and first of all, there are lots of hallucinated references that you are claiming your method is avoiding. But I'm sure that this undergrad didn't really read the literature. I just know it. And he missed the important papers. And the second is that, it's right now there are already even videos that are fake, showing people I complained about it to YouTube because there are several videos of me, and if they are reaching that level of sophistication that they can imitate, they will also reach this of writing fake papers. Now, a week ago I saw on the archive a paper that made no sense. We checked the physics, it's completely wrong, and the person who posted it is apparently a postdoc somewhere that is just piling up papers on his resume without submitting them for publication, and these are on the archive, papers produced by AI.
Yeah.
And so my question is, how do we, so as much as AI is great, it's also producing a lot of junk food, for intellectual consumption. So then we will have our AI citing papers that were produced by AI, and all of them are completely fake, So how do we cope with that?
I don't have a short answer. I will acknowledge that it is very much a problem.
Yeah.
And AI safety is an emerging field and really needs more funding at this point. Like, I think we as researchers especially should figure out ways we can incentivize people to work on AI safety so that issues like this can be mitigated. In this specific case, for example, we wanted to mitigate hallucinations as much as possible, which is why we built this. Then we had this issue of papers on the archive aren't necessarily peer reviewed and could contain, dubious quality in the thing. So right now the corpus of papers this is built from is only refereed publications. So that's sort of like, so this won't enter our training set at least. But then as more and more of these tools get made, it's difficult to say that standard will be adopted everywhere because people are usually like, I just want the largest data sets available.
Do you think people will go to primary sources? Do students or postdocs go to primary sources? Do they actually read a paper?
So I think I built this to help me find primary sources because the first week of me...
Once you know about them,
yes,
you go and read them.
I do. Because the first week I was running this, I had put out a paper myself and I searched for similar papers and it gave me a couple of papers that I did not find during my literature review. And the authors of two of those papers actually wrote to me after I put the paper on archive saying, hey, can you cite me? So I was like, okay, it's doing the thing that it's supposed to do and it's finding me papers that I wouldn't otherwise have found. I also have been working with reviews of modern physics to help them identify areas that need active reviews. So like it's applications like that, I think that this system is most useful for, where you can help target meta-analysis and reviews and determine consensus and stuff like that.
Yeah, so you're an optimist. Go ahead.
Yeah, this is great. I'm wondering kind of the last point you made about discovery. So I don't know, I use Google Scholar, not ABS, and I think it sorts its answers to my queries probably by like citation, and so the rich typically get richer. I'm curious if there's any way that you can kind of quantify the notion that maybe your algorithm is doing a better job at these hidden gems and boosting up their visibility. Yeah.
Very much an analysis I'm actively involved in. So it's essentially building graphs in this manifold of paper using ways of quantifying environment the same way we do with galaxies. So trying to find like essentially clusters in this and then find topologically similar things close to that to say this is a well-cited paper, this is a similar paper that made a similar prediction but it was before its time. And then looking for structures like that where there isn't a corresponding highly cited paper. So there's some things in here that we think are untested predictions that I think would be really cool to follow.
This is really nice. You can give credit to people that don't get credit.
Exactly.
Yeah. Please, go ahead.
When you were showing sort of a preview of some of the capabilities for like filtering these spaces, one of them was like a date. And I saw that the earliest cutoff was 1990.
Yeah, so
is there something that's limiting you going earlier?
OCR. So a lot of papers that haven't been digitized and still are images weren't in our corpus back when I made that slide. We have been working with these, they're called language vision models that can do OCR efficiently. And so I think now we go back to like 1923. So, but that was a limiting factor. I think Jill Neyman is doing a lot of work on this as well. So I can point you to something.
Go ahead, Pradeep.
Yeah, thank you. This is awesome. I was wondering if the tool allows to make predictions about which parts of this like empty space can be like in the next 10 years or become like hot.
Yeah, I mean, I think I don't know how I ended up on this slide, but this is great. This is me essentially taking that underlying space and doing a watershed to find dense clusters and then coloring each of the clusters by age. So this is showing you sort of like which are topics that are pretty well settled and people aren't doing active research on them anymore, and then which topics are very actively coming up. So this is one part where it's allowing you to find topics and topics that are close together with a valley between them where no one's working in right now. But you can also do the opposite analysis where you can look just at the valleys in the space and ask a question of, is this a valley because the instrument needed for this analysis hasn't been built yet? The theory needed for this hasn't been, developed or simulated, or something else? And I think that would be like a very intelligent way of using our current corpus to see which areas are currently not being researched and why.
But this is more like interpolating between the existing clusters, right? So I was wondering
If
it's
you
like
if you go directly outside.
extrapolate, yeah, and see what the crazy idea is.
So I currently don't trust the extrapolation based on tests that are written, and I feel like even in the interpolation, there's just so much area left to cover that we have. Because these clusters can be very different from each other, like even going from like things that are relatively close.
There is another phenomena that at least decades ago was very prominent. Every 10 years, people would write the same idea again as if it was never mentioned. Because they have a short, people have short memory. Some of them were students that were not aware of work done before. So it's interesting to check if that happens in the field where you see the same idea being done again.
Yeah, absolutely. Yeah. I mean, there's this notion of concept translation where the same concept is called by different things. And you can actually see, I don't know if I have that here. No, I don't have it. Okay. But yes, you can definitely like see if the same concept gets reinvented multiple times.
I've just got a question about hallucinations.
Yeah.
I have relatively limited experience here, but hallucinations always look like hallucinations and really way out of wacko. That suggests to me behind them there are 10 or 100 times more which are at face value pretty reasonable, but they're still crazy. So how do you deal with that?
I mean, the way we built this one is essentially to not let the LLM be creative, in some sense. So there's these like temperature parameters that you can set when you generate text, and so we use a very low temperature combined with this like corpus of text that is retrieved from searching for relevant papers.
But by the way, Perplexity is using also an approach based on the same.
Which one's that?
Perplexity.
Yeah, it does.
Yeah.
Absolutely. There's multiple now. I think there's like 5 or 6 last I checked.
John.
So I've got a question about the way that we put information into our papers.
Yeah.
So obviously we rely on visuals, graphs, figures to convey results sometimes.
Mm-hmm.
Imagine that's comparatively difficult to encode. So is there something that we should all be keeping in mind here about the importance of really strong captions that explain what the takeaways are?
100%. I think, well, okay, yes and no, because the models are, if you had asked me this last year, I would have been like, yes, captions are huge, it can't really do the images, we should be as informative as we can textually. These days, the models, like the ones that I mentioned were used for OCR, can actually read the images quite well. And so if it's a relatively straightforward image, in the sense that like it has clearly marked labels and not too many overlapping data sets, it actually does get ingested by the input scripts. So I think the way we structure information is extremely important to how it gets processed, but not to the extent that we might have thought. The other thing is like Archive's new HTML feature has also been very useful because you can render a paper as an HTML page and then you can process the images in a separate pipeline where you pass it to like a more heavyweight model to analyze.
Let's thank Kartheik again.
All right, can everyone hear me? All right, cool. Hi everyone, thanks for inviting me today. My name is Richard Pan. I'm a PhD student at Tufts University just down the street. And today I'll be talking about my recent paper on the lack of environmental quenching in a Redshift 2.6 protocluster. First, I want to talk about, give me one sec. Okay, yeah. First, I want to talk about environmental quenching. So environmental quenching can happen when a hot intracluster medium interacts with galaxies in a galaxy cluster, for example, and causes it to quench. And thereby, we see the buildup of the red sequence of galaxies. And now the two main mechanisms I'll talk about a little bit is of environmental quenching is ram pressure stripping, which happens when the infalling galaxy onto the hot ICM can strip cold gas, preventing further star formation. The second one is galaxy starvation, which happens when the hot ICM heats up the cold gas, again preventing further star formation. And now we've seen this today in galaxy clusters, low redshift galaxy clusters, but my question is, can you see this in protoclusters, or progenitors of galaxy clusters in which this environment isn't quite built up? It's not yet virialized, it's not hot and dense such that there's an ICM, and so are these environments, can they efficiently environmentally quench low mass galaxies, for example, at cosmic noon? And so today I'll talk about two main surveys that help enable this. First is the Uncover survey, which took this image of Abell 2744, leveraging the strong lensing magnification to reach unprecedented depths of around 32 AB back in cycle 1. And now this actually enables us to detect low surface brightness sources, such as low mass quiescent galaxies at cosmic noon. The second one is Megascience, which took the broadband sampled SEDs from Uncover, filled it in with all the near-cam medium bands, and thereby giving us robust and well-constrained photometric redshifts. And so now between Uncover and Megascience, we have deep data and we have good photo Zs, but now we need to make sure we're detecting sources properly. And so in this cluster, we have foreground contamination from BCGs and intracluster light. And so my task as part of these two surveys was to actually remove them like this. And this allows us to robustly detect and recover the photometry of these low surface brightness sources. And with the well-sampled SEDs and the photo Zs that we have, we can actually look for protoclusters in redshift space. And so here I show the redshift histogram of all the galaxies on the top and then all the spec Z confirmed galaxies on the bottom. And what stands out immediately is this redshift 2.58 peak that appears in both. And so we actually determined this to be our redshift overdensity, which will be in red for the remainder of this talk. And we select all the co-eval field comparison galaxies in these higher and lower redshift bins highlighted in purple. And so this redshift overdensity, though, we want to make sure is a protocluster. So to define the protocluster, we actually will use the stellar mass-halo mass relation from Baruzzi et al. 2019. And we infer that our dark matter halo mass for this overdensity is around 10 to the 13.2 to 10 to the 13.6 solar masses. It depends if you use spec Z only galaxies or you use all galaxies. And when we compare this to the Muldrew Hatch Cook 2015 paper, we use this relation, which has the galaxy cluster halo mass on the bottom in the x-axis, and on the y-axis, it's the redshift 2.5 halo mass of the protocluster. And what we find for our galaxy, for our overdensity, is that it falls within a reasonable range to be a redshift 0 galaxy cluster. And so for the purposes of our paper, we said this is a protocluster. Now we need to look for quiescent galaxies, and we do this using the star-forming main sequence from Ligia et al. 2022 by selecting all galaxies that lie half a dex below the star-forming main sequence as quiescent galaxies. This yields 34 quiescent galaxies in the protocluster and 29 in the field. And so up to this point, most other studies would determine the role of environmental quenching by comparing their quenched populations. Are there more quiescent galaxies in the protocluster than in the field? And the assumption here is that low mass quiescent galaxies, for example, in a protocluster in this denser environment would still be forming stars if they actually lived in a lower density field environment. And so to compare this, we look at the quiescent fraction, or the fraction of all galaxies that are actually quenched. And what we find is that in the low mass regime, there is a difference. The protocluster actually has a higher quiescent fraction, but it doesn't quite tell the full story. See, if we look at the quiescent fraction excess, which tells you how the fraction of galaxies that are actually quenched because of the environment they live in, we find that these galaxies, they don't make up that high of a percentage. It's a relatively low excess, and compared to other current studies as well as simulations, they're pretty in line with what we've been finding. And so this in and of itself would be interesting. We're probing the low mass regime, as noted here by the star. No other study has done it so far. But what's really unique about our medium band sampled SEDs is that we can probably and robustly estimate their quenching timescales. I know it's a hot topic right now, but, but basically the question we want to know is, are these quiescent galaxies forming and quenching on different timescales in the protocluster than in the field? And again, the assumption is that these quiescent galaxies in these denser environments have had their star formation truncated because the environment disrupts it. And so you might see a discrepancy in the stellar populations of these two populations. And so to compare this, we look at their formation and quenching time, T50 and T90. And again, comparing the protocluster in the field, in this figure, we see that there's significant overlap. The two populations roughly correspond to the same parameter space, and when we do a KS test to see if there are any differences, the p-values are greater than 0.05. And so we can't really reject the null hypothesis that these two samples are pulled from the same population. And so next, we want to look at the star formation timescale, delta t, which roughly probes how the amount of star formation that happened in the remaining time. And so the delta t, when compared to the redshift, because again, these are different redshift bins, we see that they occupy, again, a similar parameter space. We would expect the delta t to be lower, for example, for a ram pressure stripped galaxy because its star formation rate has been cut because of the removal of cold gas. But that's not what we see, and we actually, again, see that the KS test shows this as well. But the main thing with the KS test is that it doesn't actually compare the uncertainties or account for the uncertainties on our measurements. And so for this, we actually have to do Bayesian population modeling framework to infer the underlying population distributions from measurement errors. And this figure shows the population models for the for the protocluster in the field in red and purple, and then for each measurement, T50, T90, and delta t. And the green shows the overlapping area between these two curves. And again, what we see is that there's significant overlap, about 90% area, indicating that these two populations are probably pulled from the same parent population. And so lastly, what we want to check is their star formation histories, the last thing that we want to see. And again, what we see is that these two curves are pretty much identical. There's significant overlap within 1 sigma, and we don't see any differences in the shape or any differences in their peaks or valleys and whatnot. And ultimately, our conclusion from all of this evidence would be that there is no significant differences between these two populations. The protocluster sample and the field sample, these quiescent galaxies exhibit very similar stellar populations. And so our conclusion is that the protocluster environment at redshift 2.6 is not efficiently altering the quenching process. We saw this in the quiescent fraction and the quiescent fraction excess. We saw this in the formation, quenching times, the star formation timescales, and the similar star formation history shapes. And so there is no role of environmental quenching in this redshift 2.6-ish protocluster. But then the next question becomes, when do protocluster environments begin to alter quenching pathways? When does the role of environmental quenching begin to start? And so to do this, we will need to identify more protoclusters with similarly sampled medium band SEDs, such as Minerva or Technicolor, as well as continuing the analysis at lower redshift, looking for a wider range of protoclusters. Now, thank you for listening, and I'll be happy to take any questions now.
In principle, you could measure the velocities, right? You show the spread in redshift, but if you had spectra, then...
Yeah, if you have spectra too, yeah.
But and what is the overdensity that you estimate?
The overdensity. It's hard to identify the overdensity in terms of like 1 plus delta because it is such a small area on sky that we're probing, about roughly 50 arc minutes squared. And that's not even accounting for the lensing magnification, which significantly reduces your area as well as volume. So we didn't really measure the overdensity, if that makes sense.
Ramesh? Oh.
Yeah, so kind of a surprising result because I would have expected something like ramp pressure stripping to work quite well in these systems.
Yeah.
I mean, the reasons why it could not work is one, either the gas density of the protocluster is much less than in a regular cluster, or the velocity of these galaxies. Velocity dispersion is less. That you can check.
With
Is it different? I mean, this particular protocluster, does it appear to have less gas density or lower velocity dispersion compared to a fully formed cluster?
So that is a good question. We didn't exactly check that because the the spectroscopic sample here, it's actually not that many galaxies. So even at its peak, it's about 25. So, and again, this is including high mass and low mass, but most of it is dominated by the high mass end. There's actually not that many low mass quiescent galaxies that we spectroscopically confirmed, at least when I did this study, solely because they're harder to detect. We're using MSA also, so we don't even have the medium resolution to get the robust velocity dispersions as well.
So in answer to Ramesh, it may not be even virulent.
Yeah.
You don't know the overdensity.
Yeah, right.
It may be just expanding to turnaround, so there is no ramp pressure there.
Right, so that's really my question. Yeah, is that what's happening?
Yeah.
Go ahead, Tony.
Well, so this is consistent with kind of the other way of searching for this, looking at Sinyaev-Zeldovich effect and then attempting to find the cluster that is responsible for the Sinyaev-Zeldovich effect, because once you see it, you don't know what redshift it's actually at. But there are a bunch of people playing that game, and the result seems to be that there basically is no Sinyaev-Zeldovich effect above Z of 2, right? That there's
like very few.
Very few between Z of 1.5 and maybe Z of 2.1, and there's just absolutely nothing in the way of SZ effect before Z of 2.1.
Yeah. So that this sort of confirms that scenario where we don't see that many, and it would be impossible to differentiate between the Abel 2744 cluster and our Proto cluster because they're just in the same image or in the same point of view too. So it would be hard to even detect that for our Proto cluster. But in like a field sample like Minerva or like other ones that maybe you could.
This is not really a cluster, this is a group of galaxies, and they don't have a very strong imprint on Sinyaev-Zeldovich.
Yeah.
Anyway, go ahead.
I had a few, hopefully small questions. This is really cool stuff. Did you look at these galaxies in like R8X space, and do they have any structure that you see?
Again, it's hard to say, especially with lensing effects. So the purple is again the field, the red is the overdensity. You might see some clustering down here, and then maybe like over here. But again, it's hard to say. We don't have enough statistics to really make any claims there. Again, like you would want larger sample, wider area, or different protoclusters, and then you could do some comparison of the, as you mentioned, overdensity between all the different ones.
I'm just wondering if you're like diluting your signal by having too many feedbacks.
Yeah, so that was one thing that we were worried about. We try to mitigate that with the spectroscopic redshift, narrowing the window, but ultimately it would be better to have a larger sample, which is something that we're working on now.
The other related thing was, have you gone into any simulation, picked a cluster, gone back in time and seen whether at higher redshift when it was a proto cluster, whether the star formation histories were different?
Yeah, so that is also again in the next study. This was sort of letter size. The next one we want to look at galaxy TNG cluster. I'm sure some of you guys might have heard it or worked on it. Dylan mentioned that everything there is a galaxy cluster. Just pick it at the redshift, compare it. So that would be the next step for sure.
Okay, let's thank Richard again.
Is this your phone?
Oh, this is probably.
All right. Hello, everyone. I am Mesut Çalışkan. So, what happened in the earliest moments of the universe? I believe this is one of the most important open questions of physics, okay? One of the ways to answer this question is to detect cosmological gravitational waves, these relic gravitational waves from the earliest moments of the universe. In this plot, I'm showing you the gravitational wave energy density as a function of frequency versus the gravitational wave detector sensitivity for backgrounds. As you can see, there are many cosmological gravitational wave predictions that actually go way beyond over the sensitivity curves of the detectors, especially for the upcoming space-based laser interferometer space antenna. This list is not exhaustive. It's also not necessarily correct because they're predictions, yet there's an exciting prospect for probing early universe physics. But there are problems, okay? Namely, many different astrophysical backgrounds overlap over the same one-dimensional data. So how can you detect cosmological ones? You need to separate them. Because they can cause confusion, some people call these foregrounds. Okay? How do the astrophysical backgrounds form? To understand that, we need to look at first how we detect resolvable gravitational wave sources. What I'm showing you here is a gravitational waveform from a stellar mass black hole binary. The way LIGO goes for searching for them is that you look at your 1D data stream, okay? Then you have a template bank of waveforms. Then at every point in the data stream, you compute the match. And if there's a good enough match with your template bank, one of the waveforms, you filter it and you do analysis with it. But for this, you utilize the phase coherence of the waveform itself, but also it has to be actually loud enough. What happens if it's not loud enough? Well, then you cannot match and filter it. Then you have a superposition of many unresolved astrophysical sources emitting gravitational waves that superimpose in a phase incoherent way. What it means is that you cannot do this, but instead you can only characterize a stochastic background at a statistical level. You have a 1D data stream and you can, maybe constrain its variance. That's all you can do. It's very difficult. What I'm showing you here is some predictions for massive black hole binary populations from two different formation channels. I cannot get into their details, but on the left-hand side, it's a light seed formation channel. On the right-hand side, it's a heavy seed formation channel. In each plot, the vertical axis shows the redshift of a merger, so each scatter is a merger, and the horizontal axis shows the total mass. And the corresponding colors are the signal-to-noise ratios of each binary. Then you ask the question, depending on a different individual binary detection threshold, SNR threshold, rho, TH, how many of them are below or above it, and the red ones are below it. Populations are unknown. If I learn anything from LIGO, this is that. But there are predictions, and looking at many different literature, popular models, we find that there is a probability that there will be massive black hole binary background. How do we know this? We compute the energy density, omega GW, as a function of frequency. In this plot, what I show you in the red curve is the total energy density of everything, resolved or unresolved. And in the other curves, from black to yellow, I'm showing to you the background spectra as a function of frequency, depending on different detection thresholds. Okay? And computing the SNR of these backgrounds, they're actually much higher than 1. So these backgrounds could be problematic. But this is not the only possibility. This is one of the possibilities, and I might be wrong. But if you look at it, there might be an Emery background, okay, an extragalactic white dwarf background. There might be a galactic white dwarf background, a stellar mass background. At this point, frankly, I got lazy that I didn't want to put all of them. But there's a possibility for many astrophysical backgrounds in the LISA band. So the question is, how do we separate them? And if not, is it a problem? To understand if it's a problem, if we don't separate them, what I'm doing is I'm getting a cosmological background that is a power law, very simple, I know. But I vary spectral index, flat, 1, -1, and so forth. And at each one, I compute the lowest measurable amplitude of a cosmological background, okay, with or without astrophysical contamination. So the way to read this plot is that if the number is 1, it means that the astrophysical background cannot cause confusion. But if it's above 1, it is degrading your sensitivity to detecting cosmological signals. And the result is, and this range is important because for these predictions, most of them are either power laws or broken power laws living in this regime. And so if you have a flat cosmological background, you have a degradation of 10. If you have one with a spectral index 1, it's 2 orders of magnitude. So these astrophysical backgrounds could be problematic. So we need to separate them, but the current techniques are not sufficient to separate the astrophysical from cosmological, okay? So how do we probe early universe physics with gravitational wave detectors? I believe this is an open question as well. So solution, one attempt is to utilize the non-Gaussianities in the gravitational backgrounds for better separation. When I show you the energy density per logarithmic frequency bin, it is a measure of the two-point correlation function of the field. Okay, it's equivalent to the power spectra. If you have a Gaussian background, this is the optimal estimator, best you can do. But it's not necessarily the only information in an astrophysical field, because astrophysical processes at different rates with different masses are creating these. To give you an example, on the left-hand side, I have the time domain strain coming from a stellar mass black hole binary background, and in the blue, I have a massive black hole binary background. Then I'm showing you how the energy densities might look. In the regime which is sensitive for the detector, spectra look almost identical, but you can almost see difference in by eye, right? Which means that the two-point correlation function is not necessarily the one to use. So, okay, we need to get higher order statistics of the field to better characterize these. How can we do it, and to what extent can we do it? Right, to answer that question, I'm going to now quickly explore the Weyl scattering transform. Unfortunately, the time constraint is not enough for me to give you the mathematical beauty and structure of Weyl scattering transform. But I'm going to say that, okay, it's a mathematical tool discovered roughly 10 years ago that can characterize non-Gaussianity or higher order statistics of a field quite efficiently and robustly. And to substantiate this claim, what I'm going to give you is a Turing model, and pattern, an Ising model, ocean surface, I think, currents, solar surface, and cosmic matter density. Then we compute up to the 2 second-order scattering coefficients. Then I have a random model that starts from noise and generates a random field just with a single condition. They have the same scattering coefficients that I informed it with, and this is the result. So as you can see, it can capture a lot of complex features in a given field. This has been widely used in cosmology, including people at Harvard. Now the question is, can we use this for gravitational wave data? Instead of 2D, I'm just looking at a 1D field with some, hopefully, complexity to discover. First, you start simple. In this case, I'm looking at a Gaussian background, okay? I generate a Gaussian stochastic gravitational wave background, and I compare if you can do analysis with it with different summary statistics. As expected, power spectrum is best because this is the optimal estimator. But I'm showing this to tell you that you could do a similar analysis with scattering coefficients. They never get better than power spectrum because they're not the optimal case. And adding higher and higher orders of scattering coefficients, that S1 means first order and S2 means second order, is not going to improve it because the field itself is Gaussian. But a real background might not be fully Gaussian, okay? It might be very popcorny, very weird. It depends on mainly the merger rate and the underlying mass distribution. Right, so the question is, can we actually get more information? So I'm going to show you the SNR plot again, okay? And this time you can see that if you add higher order scattering coefficients, you get more SNR. To what extent this has more information requires a parameter estimation study, which unfortunately I cannot show you. But with that said, I'm going to leave you with, because I know that in this group here, there are some people that work on Weyl scattering transforms. And this is not some machine learning model that is a black box, okay? In fact, now for Gaussian backgrounds, I have derived pen and paper approach, direct relevance between the ensemble average of scattering coefficients of any order and the underlying true power spectra, as I'm showing here. I'm highlighting this because if you're using Weyl scattering transform in a numerical way and you need something to validate your tool, at least under the Gaussian assumption, you can use this analytical derivation. And you can do it up to second order. So for the Gaussian backgrounds, power spectrum is still king, and they all depend on power spectra or the functions of power spectra. All right, with that, I thank you for your attention. Thank you very much.
Thank you, Mesut. Can you explain why you can't just do 3-point function? In other words, there is only the time axis and just do 3 points?
Yeah, one is that, okay, so one is about robustness of it, one is about the efficiency of it, so I'm going to try to explain those, because there's a question, why don't you just go to the triangles or quadrilaterals? One problem is that it goes very, very big. Computing covariances become very hassle because you have very big data, okay? So one part is efficient. Scattering coefficients, I can run LISA data up to a year on my own machine without any parallelization. So I can explore things quite efficiently, and I think that matters. Secondly, there is going to be detector glitches and noises. Like these assumptions of detector is going to be Gaussian, we know from LIGO is very far from the truth. And then the bispectral calculation or trispectral calculation can be easily impacted by these, depending on their structure. But the scattering coefficient, at the cost of information sometimes, is very robust to noise. It was designed to be robust to noise. So if I actually get one frequency and put a glitch there, my scattering coefficient as a summary statistic remains, relatively speaking, robust. So in some way, and there's the third thing is that depending on the complexity of the underlying population, it might be difficult to compute the bispectra, I believe. For this one, you don't need to assume an underlying population model. You can just get the data and compute it. So there are some advantages.
It would be nice to run it on the LIGO dataset just to see what you get.
Yes, I mean, I'm applying for jobs right now, and once I'm done with the job application process, I'm going to analyze real data.
Any comments, questions?
Yeah, actually, I have a question now.
Yeah.
So, I mean, you showed that when there is non-Gaussianity,
Yes.
these other methods, your wavelet-based methods, are doing much better. For a Gaussian noise, of course, you can't do better than standard power spectrum. What I'm not able to understand is, are you making some assumption about the waveforms of the non-Gaussian signals? Are you assuming it's made up of shorts? Or can you, I mean, I'm just surprised that without any assumptions can you get such nice results.
Okay, so let's dissect this a little bit because I think it's an important point. So just to clarify, so I am here assuming for these results that the noise is Gaussian, but I cannot predict what the glitches of Lisa will be. That's a bit difficult.
That's different, yeah.
All right, we put it aside. So in this case, I'm not showing actually that the scattering coefficient does better. I'm showing that if the field, the signal also is Gaussian, the best you can do is still the power spectrum, but you can retrieve the same information. This is a test of scattering coefficient.
This is fine.
This is fine. So in the non-Gaussian case, this depends on what the field is. Depending on if I basically increase the merger rate, okay, there might be now more intermittent or less intermittent depending on that. Or if I change the underlying black hole mass function, because in the end, how long a binary stays in band is determined mostly by its mass. So then the same number of binaries can be long-lived or short-lived and therefore more or less be intermittent depending on their mass function as well. So if I actually put many binaries, the field will Gaussianate itself, then my tool is no longer useful. But it's also a way to constrain it, right? We can basically try to look at what is the scattering coefficients of my measurement and then constrain this population parameter. So the true answer will depend on that, but it's sensitive to that, and that is to use. When showing this, I'm just cheating and finding something that looks good, to be frank with you.
Looks great, yeah.
Yeah, but I can also put something that doesn't look great, and I'm honest about that.
Okay, so but to summarize, you're not assuming specific waveform, but you're saying that the method is great if the signal events are well separated. Right? If they're all overlapping, then it looks Gaussian.
Yes, that's right. Yes, but to do this calculation, I am assuming a waveform model that, yes, I am getting the regular phenomenological gravitational waveform models and generate many realizations to account for possible variance. But there is the question, what if there is an astrophysical source that we don't have waveforms for? This is something I'm also exploring because we have never detected gravitational waves in the millihertz band. There might be something that we have no idea about. And then you can still get this because it will tell you about the statistical structure of the signal. Then we need to follow it up. So it's one open question as well.
And I guess the previous comment is the central limit theorem. If you pile up a lot of independent sources, it will end up Gaussian. Yeah, so that's it.
Yeah, that's right. So if the merger rate is very high, then this tool will become not problematic. But to be honest with you, as a person working on gravitational waves, I'm happy if the merger rate is high. It means we have a lot of resolvable stuff to detect as well. So not necessarily a loss, I would say.
Yeah, but discovering new sources, I mean, this is really the deficient. As much as we are proud of LIGO that got the Nobel Prize, so forth, one disappointment is they haven't discovered a new source in astrophysics. And you know that whenever we open the new window into the universe in X-rays, radio, we always found new sources, but LIGO didn't. And so maybe you will find.
Yeah, hopefully. I'm working with Yan Dai actually on this. So I don't want to speculate because this is a very serious place. But let me tell you some. Let me tell you some limitations. So before Franz Pretorius and collaborators, I think, revolutionized the waveform models in about 2005, and I was very young then, so this is what I read. Okay, people actually had the idea of using wavelet convolutions to look for. If you don't have a wavelet template, the waveform template, that's what you do. There is still a LIGO group, to the best knowledge I have, that is doing that kind of analysis. But the thing is, they just convolve it. And if you get a field and you convolve it, convolutions are linear. You could convolve it 1,000,000 times, you will stay in linear order. This wavelet scattering transform, I'm not getting into its mathematics, but it introduces a modulus for the sake of nonlinearity, so that it gets higher order statistical structure that the regular tools cannot. Now, nobody can tell whether this method will be used, will detect something new. But it is one way to look for stuff for which we don't have waveforms for, and that's one thing that I will also explore.
Good luck. Last thing. Oh, you have? Yeah. Okay, go ahead.
So I may be missing something here, but even though when you've got lots of waveforms to add together, if they're all from the LIGO style, there's a very strong arrow of time in that. The individual object starts quiet, gets very noisy, and then shuts off.
That's right.
So is there no statistical test of looking at the ensemble data that picks out an arrow of time, or is it totally reversible?
Ensemble, okay, picks up an arrow of time. So I want to understand this question better. So first of all, whether a LIGO-like binary stays long or short depends on what frequency you look at. In the Lisa band, these things are inspiraling, and they can be in band for the duration of Lisa. So they are not necessarily chirping, right? Or they are chirping, but not necessarily strongly. They're merging in the LIGO band. So in the LIGO band, they might be this, popcorn-like thing, but in the Lisa band, they might be this stochastic background. So there's just a nuance there. Secondly, in terms of looking at an ensemble average versus a one realization, is that the question you're asking?
I'm not sure what my question is, actually. It just seems to me that the underlying elements, the smallest thing you can describe, is fundamentally very asymmetrical in time. There's no running it backwards. So how many of those do you have to add together before you lose that sense of time at all?
I see, okay, you're asking basically when does central limit theorem become a reality at what merge rate? I don't know the answer, but I think one way to actually quantify it, I can get some kind of merger rate in this axis and look at the difference between higher order scattering coefficients and the other power spectra, and that will answer the question. So I don't know the answer, to be frank, but I think there's a way to do that straightforwardly.
Was there a question, Vadim?
Yeah, no, maybe you just said it, but is it possible to improve this if you just take these templates and use them or something similar as a wavelet basis?
Yes. Thank you very much. Maybe Vadim asked me to, I was showing him the wavelets, so thank you. So these are morded wavelets. So I also use morded wavelets. So this is what you convolve your data with. Okay, it's because it's the most widely available tool, but that's not a good enough answer to use something. It's the first thing you try, but you can change it. So this doesn't really have anything informed about that stuff is happening in a non-symmetric way, right? It inspires first, then chirps, then ring down, not the other way around. Now, recently people actually came up with wavelets they want to use for glitch detection that is more informed to pick up gravitational wave signals, and there is one thing that you can use to improve this, though I haven't explored it yet because I want to first use known tools and stress test this analytically and numerically. And once I believe things work, then you have fun with it, basically. But this can be done, yes, but I'm not doing it.
Okay, let's thank all our speakers today. Have a wonderful winter break.